Welcome to the Explainer. Today we're diving into a totally fascinating, completely invisible geological engine that is quite literally running the whole show here on Earth. We're talking about the massive machinery that shapes absolutely everything, from the deepest, darkest ocean trenches to the highest mountain peaks. And yes, even the global climate system itself. It is a wildly dynamic system, and we are going to unpack exactly how it works.
So, let me ask you something right off the bat to kick things off. Depending on exactly where you're sitting right now, how fast is the ground beneath you moving? We almost always think of the Earth as this incredibly solid, immovable foundation, right? Like a fixed stage where human history just plays out. But if you look at it from a geological perspective, the crust is highly restless. It's actually a massive puzzle of tectonic plates that are continuously shifting, sliding, and crashing into one another. So just how fast is this huge planetary movement actually happening?
Get this, the sheer scale of time we're dealing with here is absolutely staggering. The U.S. Geological Survey points out that tectonic plates move at roughly the exact same rate that your fingernails grow. Yeah, literally. We're talking just a fraction of a millimeter per year for some plates, maybe up to a few centimeters for others. It is an incredibly slow, creeping pace on a human timescale. But if you give it millions of years, this fingernail-paced engine has the sheer power to rip entire continents apart and build the highest mountains on Earth. But how do we actually prove this invisible engine even existed in the first place? To answer that, we actually have to look back at an incredible accidental discovery made during the Second World War. Out in the oceans, warships were dragging these highly sensitive instruments, called magnetometers, behind them. Now, their primary mission was totally military. They were hunting for the magnetic signatures of enemy submarines lurking down in the depths. But while they were scanning the water for subs, these magnetometers stumbled upon something completely astonishing on the ocean floor itself. Instead of enemy subs, these warships detected these strange, perfectly symmetrical magnetic stripes frozen right into the rocks of the sea floor. You see, many times throughout Earth's history, the magnetic poles have actually completely switched positions. North becomes south and south becomes north. We call this normal and reversed polarity. So when hot magma rises from deep inside the Earth and cools at the ocean ridges to form brand new crust, its iron-rich minerals essentially lock in whatever magnetic direction the Earth happens to have at that exact moment. This wild discovery gave us a brilliant tool called magnetic stratigraphy. Because the seafloor is acting like a giant, incredibly slow tape recorder, scientists suddenly realized that new crust is constantly being created at mid-ocean ridges and then spreading outward. So the youngest rocks are right there at the ridge, and they get progressively older the further away you move. And here is the real shocker. The oldest seafloor we have is less than 180 million years old. I know, 180 million years sounds ancient to us, but compared to the continental crust, which is sitting at around 4 billion years old, the ocean floor is surprisingly young because it's constantly being recycled. Well, if we're making new crust, the old stuff has to go somewhere, right? Which brings us to the actual mechanics of plate boundaries. There are 3 primary ways these plates interact, and they act pretty much exactly as you'd expect. First up, divergent boundaries. This is where plates pull apart, like the Great Rift Valley in Africa. Second, convergent boundaries, where plates violently collide, causing them to either subduct into deep trenches or crumple upwards to form huge mountains. And finally, transform boundaries. That's where plates slide horizontally past each other, like the famous San Andreas Fault, building up massive pressure that eventually releases as earthquakes. That's the basic machinery driving the entire surface of our world. Okay, so keeping those convergent, colliding boundaries in mind, let me throw another question your way. If the seafloor is made of heavy, dense rock that's completely submerged deep, deep underwater, how on earth did pieces of that old seafloor end up near the summit of the Himalayas? You know, the absolute highest mountain range on the entire planet? The answer is basically one of the most epic road trips in planetary history. See, about 225 million years ago, India wasn't attached to Asia at all, not even close. It was a large island situated way down south off the Australian coast, separated from Asia by a vast body of water called the Tethys Sea. But as the tectonic plates shifted, India began this massive 6,000-kilometer sprint northward. By around 80 million years ago, it was moving at a blistering pace, geologically speaking anyway, of about 9 meters a century. And then finally, 40 to 50 million years ago, the Indian plate violently rammed right into the Eurasian plate.
Now, because both of these continents have roughly the same rock density, neither of them could easily sink beneath the other. It was like 2 massive bulldozers pushing head to head. The only way to relieve all that incredible pressure was for the Earth to thrust skyward. And what is truly mind-blowing is that this massive collision isn't just ancient history. It is happening right now. The Himalayas, and yes, that includes Mount Everest, are still rising by more than 1 centimeter every single year. That is a staggering growth rate of 10 kilometers every million years.
And hey, remember that Tethys Sea that used to separate India from Asia? Well, when those continents crumpled together, the ancient seafloor trapped between them got thrust literally miles into the sky. In fact, 50 kilometers north of Lhasa, Tibet, scientists have found layers of pink sandstone just packed with marine fossils. By studying those fossils, we know for a fact that 105 million years ago, this area had a mild, wet climate. But today, because plate tectonics violently thrust it nearly 2,000 kilometers north and shoved it high into the thin atmosphere, Tibet is an arid plateau. The plates literally re-engineered the local climate. It's just an awe-inspiring transformation.
So let's take a step back and look at the real big picture here. This endless dance of continents splitting apart and crashing back together, it isn't just random chaos. It's actually part of a highly predictable repeating engine. Geologists call it the Wilson cycle, named after John Tuzo Wilson, who was an absolute pioneer in the field of plate tectonics. The Wilson cycle essentially operates in 4 distinct stages. Stage 1 is rifting. That's where a massive continent just begins to tear apart. That directly leads to stage 2, seafloor spreading, where a brand new ocean basin is born in the gap. But eventually the cycle shifts into stage 3, subduction. That's where that aging oceanic crust gets heavy, sinks, and gets consumed back into the hot mantle, slowly closing the ocean. Which brings us to the grand finale, stage 4, continent-to-continent collision. Just like India and Asia, this is what builds towering mountain ranges. Over deep geological time, this cycle continuously creates and then destroys the world's oceans.
Now, you might be wondering, why does the creation and destruction of oceans actually matter to you and me today? Well, it's because the arrangement of the continents acts as the ultimate steering wheel for Earth's oceans. When tectonic plates move, they open and close massive seaways, which completely changes how water flows around the globe. And this brings us to a really crucial concept, thermohaline circulation. Thermo stands for temperature, and haline stands for salinity or saltiness. It's the differences in heat and saltiness that drive these massive, deep ocean currents, acting almost like giant, slow-moving rivers right beneath the ocean's surface. And all of this builds into a truly massive global system known as the ocean conveyor belt. Just imagine warm surface water traveling all the way up toward the poles, releasing its comforting heat into the atmosphere. As it hits the freezing cold Canadian air masses near Iceland, for example, that water cools down, gets a lot denser, and sinks straight to the bottom. From there, it creeps slowly southwards, deep underwater, across the Atlantic, past Africa, into the Indian Ocean, and eventually across the Pacific. This single, continuous loop is Earth's central climate regulator. It redistributes heat from the scorching equator to the freezing polar regions. And here's the craziest part. It takes a single drop of water 1,500 years just to complete one single lap. Which leaves us with this one final thought to chew on. The exact shape of our ocean basins, which channels this incredibly vital conveyor belt, is entirely dependent on tectonic plates. Plates that are moving at the exact same speed your fingernails grow. So if plate tectonics dictate the ocean's flow, and the ocean's flow dictates the climate, how will that incredibly slow creep beneath your feet right now shape the global climate of our distant future? The engine of the Earth literally never stops. It's continuously, quietly reshaping our world. Thank you so much for joining me on this explainer today, and hey, keep your eyes open because the ground beneath you is a lot more alive than it seems.